Hi, Mr. T here. In this video, we're going to go through how to work out the pH of a weak acid. Okay, so in the last video, we talked about what a weak acid is. And important to find the pH, we need to find the concentration of the hydronium ions, right? That's the most important thing. Let me just, so we want to find the concentration here. With a strong acid, the acid all completely dissociates. All of the acid particles donate their proton, and we know that whatever the concentration of the strong acid is can be used to work out the concentration of the hydronium ions on the other side. In this case, however, an equilibrium is set up. So remember that when we had a weak acid and we add it to water, let me do that again, H2O. So the weak acid and the water form a dynamic equilibrium with the conjugate base and the hydronium ion. And usually only a fraction or only a small percentage of our conjugate base and a hydronium ion on the right hand side compared to the species on the left hand side. So remember, we can write a Ka expression for this where the water is already included in the value of the Ka, so we never write it down in our expression. So we put the concentration of the conjugate base, A minus, and the hydronium ion, H3O plus, and that goes on top of the weak acid concentration. Now, when we look at this equation at the top here, any time that a weak acid here donates a proton to water, every single time that one of these interactions occurs, we get one A minus produced. At the same time, we get H3O plus produced. So what we can say is, look, if we know that every time this interaction happens, we produce one A minus and one H3O plus, then the concentration of A minus, square brackets around the outside means concentration, is the same as the concentration of H3O plus. Now we have to remember here that this is an approximation. Now why is it approximation? The reason it's an approximation is because there was actually some H3O plus present initially. Because remember, we have a water molecule will react with another water molecule. This is an equilibrium constant of water, Kw, to produce H3O plus OH minus. And at any time, the concentration of H3O plus in a neutral solution is 1 times 10 to the negative 7, right? So there is some present, but for most cases, we can ignore this because the concentration of our conjugate base is far bigger than 1 times 10 to the negative 7. So we need to think about that in special cases, but for most time this is true. Now if this is true, what we can do is wherever we have an A minus, okay, conjugate base, we can replace that with an H3O plus. So we can now rewrite our expression, which is Ka equals, now we can put H3O plus times H3O plus, because the instance we had of A minus has been replaced by an H3O plus because they have about the same concentration. Now this is quite good because what this does is that this reduces the amount of variables in this equation. So there are now 4 variables. There's now 3 variables where we did have 4. Now this simplifies, it becomes H3O plus squared over, well, get rid of that, HA. And then what we do here is we could rearrange this. Let me just go over to the right hand side here. I'm going to make H3O plus the concentration, the subject of the equation. So if I put H3O plus on one side, it will equal Ka times HA, yeah? So this is what's happened. So we have H3O plus squared. So I've moved the HA to the other side and put it with the Ka, multiplied it. But now I can get rid of the squared here. If I square root this side, yeah, then I get rid of the squared and I square root that side. So I get H3O plus equals the square root of Ka times HA. And then I just put the values in and I can work out the answer. So let's look at a specific example here. So here's a concentration of hydrochloric acid. Okay, so the very first thing I would do with this is I would write an equation. The dynamic equilibrium of this with water. Okay, so this is our weak acid. So it donates a proton. We get OCl minus plus H3O plus. Then I'm going to put this into my Ka expression. Ka equals our products, which is our conjugate base, times our hydronium ion concentration over our weak acid concentration. We simplify this, okay, well, let's do this. So now we get Ka equals H3O plus. Remember, I took the approximation here that we assume that the concentration of H3O plus is going to be the same as OCl minus, because every time we make one OCl minus, we make one H3O plus. So we still put the concentration of the weak acid underneath. All right, I'll just put here the assumption. Remember, the assumption here was that OCl minus concentration equals H3O plus concentration. Okay, and then look, I rearrange this. And I get the expression. Sorry, let's do this. So I'm going to put H3O plus squared equals, so this is on the bottom on this side, I move it to the other side, so it becomes on the top, and I multiply it times the Ka times HOCl minus. I mean, the other way to think about this, what we do is we multiply both sides by HOCl minus, yeah, by HOCl minus, and these cancel, and that's how this gets to one side by itself. And then I square root both sides. That gets rid of this square here, and it turns this into a square root. And now I'm just going to put the values in here. So it's the square root of Ka, which was 2.9 times 10 to the negative 8 times the concentration of my weak acid, which is here 0.1. So let me just work this out on the calculator. So I've got 0.1 times 2.9 exponential negative 8. Execute, and let's do the square root of that. And the answer is 5.39 times 10 to the negative 5. We want to make sure when we're doing these chemistry answers that that's at 3 significant figures. And that we put a unit here, so this is moles per liter of hydronium ions. Hey, we're not finished here because we actually have to find the pH. So I now put this, I take this answer and I negative log this answer, right? So I take the log of this, which gives me negative 4.27, and I do the negative that, which gives me the answer of 4.27. pH equals 4.27. Answer to that. Okay, so that's how we work out the pH of a weak acid. Thanks for listening to this.